So in our previous example, we started with a patch of surface, and then we came up with a parameterization for that curve, which is the boundary curve of that surface. And so that's one direction. But this is the direction that we would be able to use if we were kind of running Stokes' theorem backwards, in a sense. If we had a surface integral and we were trying to turn it into a circulation integral. But that's usually not the direction that's the most simple to use for Stokes' theorem, because it's hard to uncurl a vector field. Like most vector fields are not equal to the curl of something, and those that are, it's kind of an involved process to find what is its vector potential function. And we'd have to do those things in order to transform a surface integral into a circulation integral for Stokes' theorem. So it's more common that we're trying to do the opposite, where instead we're sort of starting with a curve, and we're interested in the circulation around that curve, and then we add the surface and we evaluate a surface integral instead. And so it's that process of going from curve to surface that is the subject of this next activity. So we're doing all this before we even get to do an integral for Stokes' theorem, just because this is a geometrically more challenging thing to do than the other curve and surface things that we've done up until this point of the semester. So in this activity, we're just being asked, and I think we'll just do part A for this, just to save a little bit of time. And what we're doing here is taking an oriented simple closed curve that's being described. So, for example, the triangle with these three vertices in XYZ space, oriented in a way that's being described here. And what we want to find is a surface such that C is the boundary, so that this curve is the boundary of that surface, and also what direction should the normal vector to that surface face so that the circulation follows the right-hand rule around the boundary that was described. Right? So that's a two-step process. And so just as an inspiration, here's what part C looks like if you do part C. That they sort of describe this curve that has four different pieces, this closed curve that has four different pieces. And when you plot all four pieces, what you find out is that they just trace out kind of this little cylindrical looking thing, right? So it's actually a piece of a cylinder that this curve is tracing out. And so then we say, well, it's tracing out a piece of a cylinder, so we might as well use that portion of cylinder as part of our surface, right? And then the only question is about the orientation. What should the orientation of the surface be? And so this is where the right-hand rule comes back in, right? And where you kind of have to imagine that here I am inside of 3 dimensions. I'm going to curl my fingers in the direction that my oriented curve is going, and then my thumb should be facing in the direction of the normal vector. And so if I do that, this is like really kind of hard for me to do, but yeah, so if I curled my fingers around that way, right, then my thumb is going to be pointing in the direction that this yellow vector there is pointing. So that normal direction is determined by the orientation of the boundary curve via the right-hand rule. So the normal vector is the thumb if the circulation around the curve follows your curled right fingers. So that's what it looks like in this sort of funky example that's in part C. So for our sake, let's just do part A together. So the curve here is a triangle with these 3 vertices with the orientation corresponding to the order in which the points are listed. Find a surface such that C is the boundary of that surface, and also figure out which direction the normal vector ought to point, given the orientation of the boundary curve that's been provided for us. So here we're given a triangle with these 3 vertices and asked to figure out what is an example of a surface which has that triangle as its boundary. And since it's a triangle, since these 3 points form a triangle, in fact, any 3 points, as long as they're not on a common line, are going to form a triangle in 3 dimensions, we can find a plane that contains all 3 of them, right, using the stuff that we learned way back in our first chapter that we did together in the course. So we found vectors that point from one pair of points to another and another one, and then took their cross product, and we got a normal vector to the plane. And then by using that as the normal vector, the coefficients of x, y, and z, we found that x plus y plus z equals 1 would be an example of an equation for this plane. And then that normal vector 1, 1, 1 also turns out to be an appropriate direction for my normal vector based on the right-hand rule. So when we look at how this triangle is being oriented here, so in the order that it's been listed to us in the way that the problem was written, that if I curl my right hand fingers in that direction, my thumb is then going to extend in the direction of the desired normal vector, which in this case points in the positive x, y, and z direction, which is what this yellow normal vector is doing. So in fact, 1, 1, 1 is the normal vector that we wanted to use here, because it's pointing away from the origin in the positive directions of x, y, and z, and that matches the right-hand rule. Another way to think about the right-hand rule, of course, is that if we look at the normal vector from its head down to its tail like this, we'll see our boundary curve flowing counterclockwise. So it's just like if you look at your own thumb on your right hand, right, that you'll see your right-handed fingers are going counterclockwise. So that's the now I feel like I'm a clown playing a trumpet or something. That's the relationship between that counterclockwise orientation that we had with Green's theorem back in the day and the right-handed rule orientation for the positive flux of a surface using Stokes' theorem.